So this is silly, but the thing is we learn about moment of inertia for area and moment of inertia for mass at the same time, and they all kind of like get, what's the word I'm looking for, like mixed up because you just call it moment of inertia. And then your professor's like, no, that's actually moment of inertia for area. Now we're going to do moment of inertia for mass. You're like, oh, it's moment of inertia because you get too lazy to say of area or of mass. So you have moment of inertia for area, moment of inertia for mass, and they're really, really, really similar. And so for me, it was just easier to make a little table and remember what was what. So that's what we're going to do. So first of all, the moment of inertia for area, you have to remember, is the measurement of basically something's resistance to bending around an axis. So specifically, everything is in 2D because it's a cross-section. So the moment of inertia for mass is actually resistance to angular acceleration around an axis, okay? And everything is going to be in 3D. So, for example, if I was going to look at a picture for the moment of inertia for area, if I was looking for the moment of inertia of area around this axis, basically I'm saying, okay, if this is a beam kind of going like this, and this is the cross-section of that beam, look at this beautiful beam, okay? Really, in real life, the beam looks like this from the side, except I guess you could kind of see there's like the I-beam part. So there's a beam, you can see it from the side. I guess I'm trying to think about how to do this. This would be coming, kind of out of the page. The question is, how does it bend that direction? That's a terrible picture. So basically what we're doing, let me try this again, is with the moment of inertia for areas, if we're looking at, I still got to draw this in 3D to some way for this to make sense. There's my little I-beam, and I'm measuring. So if I'm measuring around this axis, so it's this axis that kind of falls through there. My question is kind of like, what happens to that line as it gets under weight? So is this line going to go from like a flat line? What I'm eventually going to look at is this line is supposed to be flat, but it'll eventually look like that. But everything that you're doing in class is going to look like it's in 2D, although in real life you're doing a 3D object, but it's all about how much is it bending, okay? So I'm going to erase all these pictures, but these are good pictures. I'll just move them out of the way. I'll just leave them there. It's fine. Okay, I've got these big decisions to make. All right. So everything is in 2D for moment of inertia for area. Moment of inertia for mass, everything is 3D. So I said that it was resistance to angular acceleration around an axis. So now when you're looking at this, that was a terrible I-beam. So now if you've got this here, it's not going to be an axis on the page like that. It's actually going to be the axis going through the center, coming out of the page of the 3D object, and it'll look like a 3D object, except it's going to be longer than that. And basically what our question is so if we have this same little I-beam thing, this is why I'm not into artistry stuff. It just looks like it's flying through the air. Basically the idea is if I put a pole in here, okay, now you can't see the pole until it comes out the other side, right? Because it's pole, random pole coming out of things. So like that. There we go. That kind of looks real. So now the axis is actually going through the center. And my question is that if I like whack on this side, is it going to go flippy, flippy, flippy around the axis? Does that kind of make sense? So like if I get it really hard right here, is it going to go around? And how quickly is it going to spin around? So like the idea behind moment of inertia for mass is that clearly, just like with the bending thing, we said that it's a lot harder to bend this around that axis, that it's the axis in the center that's going to bend the most. Similarly, or the easy, not the most, but it's going to be, you know what I mean? That's where we're going to see the line of neutrality. That's the important part. Similarly, if I'm trying to spin something, it's going to be a lot easier to spin it around its center than if, say, I was going to put a pole. I was starting to put it over there, but just to make a point, I'll put the pole all the way over here. Like if I stuck it into this little corner slot and it came out there, that's going to be a lot harder to kind of get it around. And you might think, well, yeah, that makes sense, because if I'm trying to spin it around this spot right here, I've got a lot more of a heave-ho to get this corner all the way around because it's heavier and it's further away. Whereas whenever I'm in the geometric center of the cross section, then everything's kind of equally distributed. So, it's the same level of heave-ho-edness to get all the way around. And that's basically what we're looking at. So what's going to be cool is in statics, you had the sum of the forces is equal to 0. Well, in dynamics, you'll have the sum of the forces is equal to mass times acceleration. But in so far as the moments, you're going to have the moment is equal to the mass moment of inertia times angular acceleration. So this, just like mass, you can think of like something's heavy. I don't know why this box is particularly heavy. I'll draw it in a dark color so it's heavy. Heavy box. It's a sad box. It's heavy. So this box is harder to push the heavier it gets. So it's resisting change. It's resisting acceleration. Similarly, if I have some really big, giant, clunky beam, the clunkier the beam, the more it is going to resist rotation around the axis. And so that's what that is. So alpha is angular rotation. Like if something's rotating, that's alpha. Well, really, we'd have it going the other direction. But that's basically the biggest difference. Conceptually, that's the most important thing to understand is that the moment of inertia for area is directly related to bending, and the moment of inertia for mass is in no way measuring the same thing. It's not like, oh, well, one's just in 3D. I mean, one is in 3D, but it's doing something totally different. It'd be like saying, okay, so this one is like, I don't know, like processed cheese, like the cheesy powder that comes in the mac and cheese box, and then you'd be like, and this is ice cream, but it's the same because they're both kind of like milk. That's ice cream, apparently. I mean, yeah, I guess they're both kind of a milk product in some way, but ice cream is totally different than orange cheese. So orange cheese powder, nonetheless. So anyway, they look similar insofar as the equations, and they work similarly mathematically, but at a fundamental level, they are completely different. So this is really, really important. All right, they even look very similar in their equations. So you might have I about the x-axis as being how the y squared area is distributed, or I about the y about how the x is distributed around the area. Or you might have the polar, how it's all distributed, again, from the area. Now, in the moment of inertia for mass, it's actually got a slightly different symbol, but not enough that you might notice. But it's all going to be about how far the mass is from that center. So if I'm doing I around the xx axis, around the x-axis, that's going to be how my y's and my z's are centered with respect to the weight. So how is the weight distributed? So again, if I'm kind of thinking about this, if this is like my YZ axis, and this is X going through, how is this piece distributed, and how is this piece distributed, and how is this piece distributed, and how is this piece distributed? Okay, so that's what we're looking at there. So with the IYY, again, the equation is just R squared dm, but in this case, R squared is given by X squared and z squared, because x squared plus, so it's radius. Similarly for IZZ, R squared dm, now it's going to be X squared and Y squared dm. So again, d mass, not d area, because this is a physical object and not just a cross section. You have the radius of gyration. Actually, I'm going to put that in the center because the radius of gyration is called the same thing for both of them, and they're both called k. I can't fix it. It's just the way it is. But if you're talking moment of inertia for area, then the moment of inertia of area is the area times the radius of gyration. If you are in mass, it's going to be that I is equal, instead of being area, it's going to be mass kg squared. So those are very similar. For parallel axis theorem, if you are moving to some random place on X, then you're going to start at the centroid, and you're going to do like the delta Y squared times the area, and similarly for Y and Z, or J or whatever, I guess Y and J. And then for the moment of inertia for mass, it's going to be I of this new place is going to be starting I at the center. And then again, you're moving by the distance, but you're multiplying by the mass. And this is always confusing because most books are just going to call it d, and then it looks like d squared, and it looks like you're starting to take the second derivative of m, but you're really not. So you could also maybe write it as r squared or delta r or something. Anyway, another thing that makes them different is that the moment of inertia for area is measured in usually quartic millimeters, or you could do quartic meters, or quartic feet, or quartic inches. On the moment of inertia for mass, because it's a mass times an area, you're going to end up with kilogram meter squared or slug feet squared. So you're going to get very, very different, very, very different values. Now, if you're having to do these kind of from scratch, an important thing you need to remember when you're doing integrals, remember that dm is equal to rho dv. But the rest of the math is actually pretty similar. So hopefully that will help you kind of keep everything straight, and just kind of give you an idea about about how this would look. But the biggest thing I think to remember as the difference between these two things is that you're just fundamentally measuring a completely different value for each one.